Now, imagine this, right? You are actually looking at this comet, the size of Earth kind of a comet, flying across our solar system. Like, think of like size of Earth object flying across our solar system, or size of Mars flying across our solar system. That is the kind of level of thing that we are dealing with. So this is the data that I captured this morning. I just did a star alignment so you can see. Nothing much. We wanted to zoom in and it is kept moving, so I wanted to zoom in further, coming back like in a loop, right? Because the time lapse is so long, that's what it is doing. By the way, I took pictures of Comet Swan as well. It's a long story. I need to make a separate video on that one. So I wanted to focus right now on this one because this is really good.
It began like any other night of observation. The skies above Hanikaha, Hawaii, were unusually clear, and the Seastar S50 telescope, an instrument favoured by serious amateurs, was quietly aligned with a faint object drifting through the solar system. At the time, 3i Atlas wasn't expected to offer anything new, just another interstellar visitor catalogued and tracked. But then the exposures came in, and nothing looked right. The images showed a long straight filament extending from the nucleus, not away from the sun, as every comet ever observed had done, but directly toward it. A razor-thin anti-tail held together in defiance of solar wind, radiation pressure, and the chaotic outgassing expected from an object of this size and speed. It wasn't just strange, it was unexplainable. Multiple exposures were taken. The object was tracked over 2 nights, different angles, same result. What appeared on the screen wasn't noise or lens flare, it was real structure. The AI-assisted stack confirmed the vector, sun-facing, clean and stable. At first, the operator assumed it was a software error, but it wasn't. The structure didn't waver, it didn't bend, it persisted. At this moment, the telescope became more than just an instrument. It became a witness, not to a theory or a rumour, but to raw data that no textbook could explain. And this was just the beginning. Within 24 hours, the image was shared among independent astronomers. It didn't take long before the question emerged. If an amateur telescope could see this, why hadn't NASA said anything? And why was this razor-straight tail being ignored when every law of physics said it shouldn't exist at all? Whatever this object was, it had just stepped out of the known and into something else. When the Hanikaha images began circulating through astronomy forums, the response wasn't immediate. Most professionals assumed it was an artifact, perhaps a stacking error or processing artifact. But as more frames appeared from different sources across the southern hemisphere, one pattern held true, a sharp, coherent anti-tail that pointed directly toward the sun, remaining fixed across observation windows and telescope systems. But NASA said nothing. Despite tracking 3i Atlas through its JPL Horizons database, despite publishing orbital paths and acceleration curves, there was no public mention of the tail's unusual geometry. No analysis, no speculation, just silence. To some, that silence was a form of caution. Large institutions are bound by peer review processes. Claims require verification. But to others, especially those watching this object from their own backyards, the lack of acknowledgement began to feel intentional. Why wouldn't the agency release even a single statement on a feature so geometrically perfect, so contrary to expected dust behaviour? If this were a natural outgassing event, wouldn't that in itself be worth highlighting? What emerged instead was a subtle shift in narrative. Observatories were instructed to focus on brightness, acceleration figures were updated, exposure times were re-optimized, but the tail? It remained off-topic. That's when the community of independent observers began organising, not as conspiracy theorists, but as data collectors. If official channels wouldn't acknowledge the anomaly, then perhaps it would have to be confirmed by those outside the mainstream. And so began a race, not for fame or headlines, but for truth. Because what we were seeing wasn't a theory. It was geometry, light, dust, direction. And if that geometry didn't match our physics, then it wasn't the telescope that needed recalibration, it was the models. In comet science, tail orientation is among the most fundamental observations. Solar radiation and solar wind always push material away from the sun, creating the signature coma and trailing tails we associate with icy bodies. This behavior is so consistent, so universal, that it's practically assumed in every orbital simulation. Until now. Because 3i Atlas doesn't obey that rule. The Hanikaha images didn't show a tail arcing behind the object as it fled the sun's influence. They revealed something deeply counterintuitive, a long, sharp projection extending toward the sun. This wasn't a brief flash or a curved dust band caused by perspective. It was a fixed structure, spanning possibly millions of kilometers, oriented directly along the sunward axis. Some tried to dismiss it as a projection illusion, arguing that Earth's position in the orbital plane might make dust lag appear like a tail. But orbital simulations disprove this. Earth never crosses the object's orbital path. There is no known geometry that would cause this inversion, and even if it were a projection illusion, the tail would blur, fan, or distort over time. But this one doesn't. It stays consistent, straight, sharp. It responds to solar alignment, not to orbital perspective. That left scientists with a narrowing set of possibilities. Could outgassing be so violent it pushed dust forward? Unlikely, not at this distance. Could particles be massive enough to resist solar push? Only if they were made of dense material, perhaps metallic. Or was this structure something else entirely? Because a tail that points the wrong way isn't just a photographic anomaly, it's a physical contradiction. And when contradiction persists in real data, it forces a question few are prepared to ask. Is the object obeying natural laws, or is it telling us those laws aren't complete? As more frames poured in from telescopes around the world, researchers began comparing datasets. Spectral readings, brightness curves, and tail consistency were analysed side by side, and one characteristic became impossible to ignore. The material forming the anti-tail was far denser than anything typically ejected by a comet. In natural models, comet tails are chaotic, composed of volatile gases and loosely bound dust. These particles are easily influenced by sunlight, radiation pressure, and gravitational shear. They scatter, expand, and fluctuate. But the material from 3i Atlas didn't behave that way. The anti-tail wasn't just long, it was narrow. Impossibly narrow for a dustband that should have been dispersed. That meant two things. First, the particles were unusually uniform in size, and second, they had to be very heavy. Simulations run at independent labs showed that only metal-rich grains, with high mass-to-surface ratios, could remain aligned and undispersed across that distance. These grains would need to be nearly identical in shape and density, far too precise for typical comet outgassing. This hinted at something deeper. Either 3i Atlas had a metallic core, or it was sorting particles in a way no natural body had ever demonstrated. And that raised more questions. Was the material being released, or was it being directed? Was this a natural sorting effect caused by unique formation chemistry, or something engineered? Because in order to explain the anti-tail's coherence, nature had to be uncharacteristically perfect. That's not how nature behaves. Chaos is normal. Imperfection is standard. The deeper we looked into the density distribution, the more it resembled precision, not randomness. And that meant one of two things. Either we'd discovered the most stable natural dust ejection ever recorded, or we were watching a structure that wasn't meant to break apart. A comet's spin tells a story. As they rotate, comets expose new surfaces to the sun. That heating causes outgassing to fluctuate, often producing jets or flickering in the tail. It's common, predictable. But when independent analysts measured the rotation signature of 3i Atlas, something didn't add up. The object does rotate, roughly once every 16 hours. That's known from repeated light curve measurements. But despite that spin, the anti-tail remains unbroken. No stutter, no pulse, no indication that outgassing was changing with the exposed surface. In every natural case, this rotation should cause visible ripples. Dust jets would sweep like a lawn sprinkler, creating spirals or curves as the comet tumbles through space. But here, the jets, if they exist, don't move. The anti-tail is a perfect blade suspended without motion. That leads to two possibilities, both problematic. First, the object might be ejecting material only from one fixed point, which remains precisely aligned during every rotation. But that's unlikely, unless it's shaped in an extraordinarily symmetrical way, or has an internal mechanism for controlled release. The second possibility is even stranger. The material isn't reacting to rotation at all. In other words, the tail structure is decoupled from the surface's changing orientation. That suggests confinement, stability, a phenomenon closer to propulsion, exhaust than passive dust shedding. It's the kind of structure you'd expect from a craft, not from a comet. And yet, the object continues to spin, and the tail continues to defy that spin, almost like it's stabilized from within. Whether magnetic, inertial, or engineered, the anti-tail's refusal to respond to rotation stands as one of the clearest signs that we are not observing a typical celestial object. It's a contradiction, and contradictions are the seeds of revolutions in science. Reflectivity doesn't always mean simplicity. When researchers first measured the brightness of 3I Atlas's anti-tail, they noted something odd. The reflectivity was high, similar to what we'd expect from ice particles. That would normally suggest the structure is made of volatile grains, likely water or carbon-based ices. But that didn't match its behavior. To maintain the tail's razor-thin form across millions of kilometers, those particles would need to be massive, too massive to be pure ice, and too stable to be typical cometary dust. This contradiction became known as the ice-metal paradox. The most likely model to emerge was a hybrid, ice-encased metal grains. This formation, though rare, could theoretically occur in the outer regions of a protostellar disk, at the boundary where heat drops low enough for water to freeze around heavier elements. In such an environment, iron-rich cores could form with volatile shells. As those grains approach the sun, the ice sublimates, releasing the metal grains in a uniform stream. If the object's orientation and rotation axis are favourable, those grains would naturally settle into a flat orbital disk. And that's exactly what we see. The model explains the brightness, the density, and the blade-like geometry. But it also means we're not looking at a comet in the classical sense. We're looking at something closer to a fragmented planetary core, perhaps ejected during a collision in another star system, preserved for eons, and now passing through ours. That hybrid behaviour, part ice, part engineered metal, forces us to confront a deeper truth. This object doesn't belong here, and it doesn't behave like anything that was born in the solar system. Whether natural or artificial, it's telling us one thing very clearly. Its origin was violent, its structure is intentional, and its story is not over yet.